Why don't rocket engines melt? How engineers keep engines cool. If you stand next to a rocket while it takes off, you will instantly vaporize due to the extreme levels of heat being released. However, the astronauts and the spacecraft itself, from its engines to its outer body, remain intact. It all happens thanks to the state-of-the-art cooling systems. Today we'll be talking about these cooling systems and the facts that why don't the rocket engines melt. What are the different types of cooling systems involved in the making of a rocket that prevents it from melting due to the intense heat being discharged? Most importantly, how do these cooling systems work? Well, stick around till the end as we answer these intriguing questions. Without further ado, let's begin the video. The temperature of gases inside an engine's combustion chamber can reach extremely high temperatures, around half the temperature of the sun's surface and well above the melting point of most materials. Rocket engines must achieve this temperature to operate properly, but how will they do so? In today's video, we'll discuss the various engine cooling technologies needed to keep rocket engines from melting. Firstly, we have ablative cooling. This approach makes use of a material that vaporizes and then dissipates, taking the heat with it. Typically, this is built of carbon composite, which has a very high melting point. Now, how can this be used to counter heat? Most spaceships are built like this. After a coating of the heat shield is applied, it gets extremely hot after the craft enters the atmosphere of the Earth. However, in response to the heat, only the layers of the shield absorb the heat, keeping the spaceship cool. Due to the layer, the heat does not reach the spaceship, keeping it safe from harmful heat. Similarly, a rocket engine can be cooled using the same approach. A layer of carbon composites covers the combustion chamber and nozzle walls. This carbon layer will slowly be burned away as the propellant burns in the engine. This technology is exceptionally efficient and reliable for cooling engines because it has no moving parts and is self-regulating. However, not everything is perfect, and there are significant drawbacks. The most prominent of which is that an engine cooled in this manner cannot be reused. Because the ablative chamber walls wear down, certain engines won't be able to go through testing before being employed. As you can see, there are significant downsides to the ablative cooling method. Don't worry, because we have more cooling methods planned for you. Secondly, we have radiative cooling. When fueled rocket engines flash brilliant red because the metal gets extremely hot and radiates the heat into space. There is no air to pick up and conduct heat away in space since there is no atmosphere. Instead, engines can radiate heat out from their nozzles because radiation does not require matter to transfer heat, just like the sun, which uses radiation to transfer heat through space's vacuum. The nozzle extensions of vacuum-optimized rocket engines are made of an extremely thin metal, typically a niobium alloy, that can endure severe heat holds. This helps in dissipating heat. The disadvantage of these nozzle extensions is that they are extremely thin and brittle. Furthermore, because niobium is highly reactive to oxygen, it can only operate in a vacuum, making the engine more complex to manufacture. Thirdly, we have perhaps the most prevalent and commonly used method of preventing a liquid-fueled rocket engine from melting. This begs the question, what is regenerative cooling and why is it the most used method? Regenerative cooling involves passing some or all of the propellant via the combustion chamber and nozzle walls before entering the chamber through the injectors. While the walls and nozzle of rocket engines appear to be thin, they have small channels through which fuel can be run to keep them cool. Now for the interesting bit. This approach allows the fuel to boil before it enters the chamber. The expander cycle is a technique that can be used to spin the turbine and drive the engine's pumps. The cycle uses the thermal expansion of the fuel as it transitions from liquid to gas to power the pumps. Moreover, the expanded gases take away the heat from the surroundings, thereby keeping the exterior cold. Next comes the heat sink approach for cooling. You must be thinking the method must involve something to do with heat sinking. The combustion chamber and nozzle are built of a high conductivity material, commonly copper, and thermocoupled to detect temperatures buried in the thick, uncooled wall in the heat sink method. This high conductivity metal sinks the heat from the rocket walls, thus keeping it cool. Heat sinks, however, have several significant drawbacks. Weight is one constraint. When creating a rocket, weight reduction is critical, and an additional thick metal wall will add a significant amount of weight. Another concern is that an engine can only run for a certain amount of time before all of the metal in the engine melts. This method is cheap to apply initially, but the cost for its renewal is very high. So are you guys enjoying the video? Do like it if you do. Now here comes another challenge. Which of the cooling methods is the best one for rockets? Do you think that there are any other methods that haven't been mentioned in this video? Are these changes and reviews enough for mankind? It seems like many people have complimented the effort for piling this with me. Film cooling is the next most frequent type of engine cooling. A fluid is injected between the combustion chamber and nozzle surface, as well as the hot combustion gases. In this manner, this can be done with liquid or gaseous propellants because fluids are either gas or liquid. The goal is to create a thermal barrier between the wall and the hot combustion gas, with cooler fluid in between. The technique to cool a liquid film is to have a higher concentration of fuel injectors on the injector's face outer perimeter. Fuel is normally favored because the main combustion chamber is fuel-rich. There will be a ring of additional fuel flowing around the outer perimeter that won't have enough oxidizer to react with. This means a ring of rich fuel combustion will be present to prevent heat transfer from the primary combustion gases to the walls. When a carbon-based fuel is used as coolant, it generates a carbon layer along the walls in the form of coking. A lot of carbon is left unburned in fuel-rich combustion, which can result in soot. This may be seen in many engines' gas generator exhaust. SpaceX runs a gas generator highly fuel-rich in this engine, which lowers the temperature enough to prevent the turbine from melting. As a result, the exhaust is particularly dark and sooty. This soot can also adhere to the chamber's inside walls. However, despite there being soot, the temperature has dropped and thus succeeded in its job. As you can see, we've discussed many methods involving cooling systems in rockets that are essential to the workings of a rocket. Many space-based countries use different methods for different rockets, depending on a variety of factors, such as weight, size, and most importantly, their budget. Normally, many companies opt for the regenerative cooling method as it is the most effective in cooling down the rocket. Moreover, it's not that pricey and can be used for a long time since it does not regress as time goes on. The rest of the methods are also commonly used by rockets, but as of the start of the year, the price of the dollar was comparatively less than what it is now. We hope in the future more systems are made which would make space travel reach the massive untapped potential it has so long predicted. One needs to comprehend the possibilities that are available to him in terms of space travel. He or she shouldn't be bound by the limits of human thinking, thus one should broaden his creativity and look for new ways the current technology could be improved, such as the engine cooling, which will open a million more opportunities. So what do you think of the various cooling systems in a rocket? Doesn't it amaze you the technology behind this technology? Let us know in the comments below. And if you want to watch more of our amazing videos, then stay tuned.